what we got to last time was we had our hydrogen molecule Hamiltonian, where we said we were only going to do it for one electron. We made some guess function that was a combination of those hydrogen-like wave functions. We went through a pretty lengthy process, variation parameters, set up that secular determinant, set up a bunch of integrals, and said sure we could solve those if we had to. They all depend on the distance between the nuclei. And we got two energies out of it. We got an E5 plus and an E5 minus for the addition energy and the subtraction energy. And we said we could represent that as if we had our hydrogen-like wave functions. We had one that dropped in energy and one that increased in energy. And we said, okay, this is something, and when I drew this picture, there was a collective, oh, when we got to that part, because this is something that does look familiar to us. Normally we do it in this kind of nice, pretty picture, where we have the one of the original atoms represented on one side, one of the original atoms represented on the other side, and these middle things. Just to be clear, these middle things are what we use to start defining these molecular orbitals, or an orbital acting over the entire molecule. This is a relatively simple molecule we're looking at this time, and we didn't actually finish the last bit, which was solving for C1 and C2. That process, I want to do it in a little bit of a different way at the end of class using a computer, but it's essentially going to be a matrix diagonalization. In this simple case, we could theoretically get the two equations with the two unknowns we had before, pick our first energy and plug and solve, pick our second energy, plug and solve, and we end up with two cases. For our E5 plus, we end up with C1 equals C2, which is going to give us our phi guess is going to be equal to psi 1sa plus psi 1sb. Right? We get this cooperative type situation. For our other possibility, E5 minus, we get C1 minus, C1 equals negative C2. Or our phi guess equals psi 1sa minus psi 1sb. And we can look at these and we can say, okay, this is not that surprising. We have some positive interaction, some negative interaction. We've got the wave functions kind of interacting in a good way with each other. We have some the wave functions interacting in a subtractive way with each other. And we can make pictures. We can take these, since we know these wave functions from our handout, we can actually make plots of what that looks like if we wanted to. And we get two pictures. One of those pictures looks something like this, where this would be where nucleus A is, this is where nucleus B is, and that distance between them is that distance r between them. And we can see as we change this internuclear distance, the way this picture, how much we have overlap, how much we don't have overlap, that picture is going to change. Because remember, all of these integrals, after we go through all the trouble of that, they just depend on the internuclear distance r. This would be for that additive case where there's cooperation between the two atomic orbitals. So this would be for our psi. I'm going to call this the phi plus case for that additive energy. And we could also have this case for that subtractive energy, that negative case. So we've got same sign, opposite sign. Now this isn't psi squared, this is just psi, so you can see really obviously that they're opposite sign. And the important thing here, I'll label this one phi minus. And the interesting thing about this is we have a zero crossing, right? That's going to create essentially a space in between our two nuclei where we have 0 probability of electron density. If we drew this as the size squared case, you could make a picture that essentially looks like something that drops to 0. You end up with just a complete hollowed out section in between where you have no electron probability between your two nuclei. Again, this is still nucleus A, this is still nucleus B. There's still a distance r apart from each other. But in this other energy case, this phi minus case, there's no probability of the electron. This plot says there's no electron there. That's part of how you could rationalize that this is going to have this higher energy. There's going to be some more repulsion there between the two. But the thing I really wanted to do today was talk about what we can do with this. We spent quite a bit of time going through variation of parameters. We spent quite a bit of time setting up this simple case. And now we want to start thinking about, okay, so what else can we do with this? Much in the same way that the hydrogen atom wave functions were able to build to like helium, we can use this idea to build to more complicated situations. So let's go through a few cases where we can do more complicated things. And essentially what we're going to be doing, and I'm going to erase most of this, mostly what we're going to be doing is we're going to be focusing on how can we change this guess function to get different situations, and how is our Hamiltonian going to change for these different situations. And before we get to how the Hamiltonian changes, I'm just going to give a couple of the conditions of what we can do now. What else we could do. Thing number one. We can increase the number of functions and parameters we have. We can think about this in a couple different ways. We can think about increasing the number of parameters and functions we have as essentially adding another nucleus. So we can increase this to having 3 nuclei, 4 nuclei, 5 nuclei. We can increase the amount that we're going to be doing. The other way we can think about this is we could also say, actually, this second nucleus, I also want to include the fact that it has some p orbital properties. So we could add another C3, and we could do a psi 2pb. We could add other wave functions to kind of complicate the second orbital, which pretty much, that's going to lead us to the third thing, which is making each of these sides more complicated. But I want to talk about something else first, which is closely related. The other thing we can do, we can totally change the size. And we saw an example of this about a week ago when we were doing that hydrogen-like case. We can make them Gaussian functions. Rather than using this set of functions, we can use Gaussians. We can use all kinds of other types of guesses. This really is what leads to a lot of what happens in computational chemistry, the computers. We'll often throw out the hydrogen basis set, the set of hydrogen functions we use, and pick a completely different basis set. Quick check, 1 through 5, familiarity with Chem draw. Do you remember that part where you would do analyze, and you'd have to pick a basis set? And you'd pick like 311G or 6-311G or some other set, or you pick STO. That's this, right? When you were doing that in ChemDraw, you were actually picking a basis set to do variation of parameters. The computer was taking that basis set and essentially doing all of the mathematics. Now, there's pros and cons to this one. The pro is that computers can do a lot of quick math. If you put Gaussian-type functions or other types of functions, the computers work with them really well. The con to doing this one is we lose all of that chemical intuition that we have around the systems we pick, right? by picking hydrogen-like wave functions, we already have some familiarity with what those functions look like and what kind of problems they solve. So having the hydrogen-like wave functions gives us some chemical intuition for what may or may not work. These, way better in computers, but we lose all of that intuition, and we're kind of just throwing spaghetti at the wall and seeing what sticks at that point. Number 3, which kind of skips over that, and is the thing that we're really going to, part of the thing we're going to focus on today, so the other thing we can do is we can make each psi more complicated. Right, so instead of just doing psi 1sa, remember this was for one electron, so we didn't have those Slater determinants. One of the things we could have done is we could have said, hey, what if I wanted to do this for 2 electrons? Then each of our psi's, instead of being a simple psi 1sa, would have to be a psi 1sa alpha 1, psi 1sa beta 2, plus the next part, plus the next part. We could actually make each of those functions a Slater determinant, guaranteeing that we have that asymmetry. This is also part of what we do in hybrid orbitals, is we make each psi more complicated. And we're going to talk a bit about hybrid orbitals. Hybrid orbitals kind of have some pros and cons to them. One of the cons to hybrid orbitals is you already need to have some information about the system you're working with. You can't start with a blank slate. You already need to know something about the geometry and the structure of what you're doing in order to get a good hybrid orbital. But we'll talk about that more in just a moment. So let's do some examples of this third one. This third one's where we're going to focus today. So what are some complications? Here's a complication we could do. We want to do something that's relatively simple still, so we're going to look at a diatomic. And I want to make my wave, I want to make my guess function a little bit more complicated by changing those psi's. And I can look at lithium hydride and say this is similar to what we did, right? I still have 2 nuclei. But in this case, the lithium is going to have 3 electrons, the hydrogen is going to have 1 electron. So I'm going to have 4 electrons. In that case, I can make a phi guess. Okay, how much of this do I want? I'll write out some of it. For electron 1, 2, oh wait, let's see. 1, 1, 1. Right, and essentially what I'd have to do is I'd have to make an entire 4 by 4 of this. Right, so then I'd have my 1sa alpha 2, my 1sa alpha 3, and my 1sa alpha 4. This would be for a 2 electron case. We haven't seen something like this yet, but I could fill this all out, and then I would have plus C2, and I would have another 4 by 4 matrix here. That's one way I could make it more complicated. Yeah?
So for the first matrix, it's a 2 electron system or a 4 electron?
So this is a 4 electron system, all centered on nucleus A. This is going to be another 4 electron system, all centered on nucleus B. Each of these matrices, I hope I stopped a couple of you from solving this Slater determinant. You were just supposed to set it up on the quiz. This is going to have 24 terms. Right? So there's quite a bit that goes into that. This is a significant increase in the complication of our functions. And in fact, you could also increase the complications here. You could also do a plus a C3 and a plus a C4, where I'm changing my alpha and beta order for each of these. So there's some more interesting things that we could do here. this, as you can tell just by the setup of this starts to get a little bit heavy very quickly, which is part of why people started coming up with tricks, different ideas, using that chemical intuition to kind of simplify these things, which gets us to a second example. Which is going to be hybrid orbitals. Particularly, I'm going to be looking at BH3. I'm doing this one in particular for a couple reasons. One, I really want to get sp2 hybrids for the thing that we're going to be doing at the end of class. And two, it's a really simple thing to try and do an example of, right? I picked something that only has a few things attached, has as few electrons as possible while we're doing that. And one of the main tricks we're going to use here, I'm going to redraw this as the molecule. And I just can't help myself. I'm already drawing it with the geometry, which is part of how we get the hybrid orbitals. But we're essentially going to split this into 3 separate 2-center problems. I'm going to do a problem there, where I'm going to have some function. I'm going to pick something different than the phi's I picked before. That's going to have phi 1 associated with it. I can pick a function here. That's going to have a second problem associated with it. And I can pick a problem here that's going to have a third thing associated with it. Now, in order to get this to work, the hydrogens are the easy part, right? So when I put together my guess function for this, I know I'm going to have something that's going to have like a C1 psi 1s on hydrogen A. That part's the easy part. Hydrogen only has that one part. The part that gets a little bit more tricky is, what do I put for boron? And this is where the hybrid orbital theory actually comes in. Instead of just putting anything there, I'm actually going to put an entire set of functions here. And I'm going to write these, and then I'll explain how this comes about. And I have to put a prime because I already used a C1 there, so that's a different C1. This function is picked with chemical intuition already built in, right? So for the boron, we didn't take into account the core electrons. There's 2 1s electrons that we didn't take into account. And if we looked at boron, we would say, well, why would you have 3 electrons like this? Why wouldn't you have a psi 2s alpha, psi 2s beta? When we think about this, that's the natural intuition to come up with, right? You look at the periodic table, you say, you look at the electron configuration for boron, you say it's the outer electrons is a 2s2, 2p1. But remember, that's completely built on saying everything is hydrogen-like. And we want to find somewhere where we can talk about this molecule where we're going to have extra interactions. Question?
Is that a beta in the C2 term?
C2?
Yeah.
A, psi 1, no, that's just a B.
Okay.
That's just a B. So that's a parameter. So essentially, this has 1, 2, we can actually 1, 2, 3, 4 parameters in this equation. So we've done 2 things here. One, we've said I can just do this one bit of problem. I can treat the hydrogen just as a 1s, and I can treat the boron just treating the valence electrons, and I can make some special guess. And this is, in my opinion, the big problem with hybrid orbital theory. You need to kind of already know the geometry you want to get in order to guess this function. In order to get that, you already need to know something about the geometry you're trying to get. It does have some important historical context, right? The hybrid orbital theory was one of the main ways that we were able to start to describe entire molecules. It plays heavily into our chemical knowledge of the systems already. But you do need that kind of existing information in order to do it. And while this might still look complicated, because I still have to write two more things like this. I have to write another function for this problem and another function for this problem. That's still going to be less complicated than doing 4 nuclei with all of the electrons. Question?
How would this work with the trigonal planar, not like a planar molecule? So it has 2 like lone pairs, or it has a lone pair?
Oh, so if you had a lone pair,
yeah,
you would still you would treat that lone pair on the boron. Right? Those electrons would be in one of the boron orbitals. So you'd essentially have a function that doesn't have that hydrogen part. Right? And you would still treat that as electrons around the boron. So this is going to create 3 problems. Each problem is going to have 4 parameters. It's still a little less complicated than doing a whole bunch. Let's see, how many electrons is this? 1, 2, 3, 4, 5, 6, 7, 8. This is still a little less complicated than doing 4 8x8 Slater determinants, which would be the other way to do this. So using that, we get some simplification. And most importantly, this starts to provide a structure for us to look at more complicated problems, which is really the thing I wanted to get to today. So where we can start to do some really interesting problems, or, you know, in my opinion, we could start doing interesting problems back there with the lithium hydride, but we would be using computers to do that, right? This one, we're also eventually going to use computers, but it's all about how we use that chemical intuition to simplify our guess functions, figure out which things we can ignore, which things we need to consider. So this is going to be 4th thing. Sorry, 3rd thing. Huckel theory. 1 through 5, you remember something about Huckel theory. Ooh, that's more zeros than I was expecting. Okay, so Huckel theory is, again, just like hybrid orbitals are a particular system, Huckel theory is going to build off of hybrid orbitals in this idea of how we can create some function out of hydrogen-like wave functions to describe a single atom interacting with other atoms. Huckel theory is going to build off of that. It's going to be particular to conjugated pi systems, things that have double bonds, things that have hybrid orbitals right next to each other. Particularly, it's going to be really useful for these situations, these conjugated pi systems. This would be an sp2 hybrid, so named because we made it out of an s and 2p wave functions. And what we're going to look at is the electrons inside of the hybrids versus the electrons outside of those hybrids to figure out what we can do. There's a couple assumptions we have to make inside of Huckel theory in order to get this to work. And again, this is all built off of some level of chemical intuition and some level of understanding that's going to allow for different functional guesses and simplifications. Thing number 1. The single bonds, all of the single bonds inside of this conjugated system, that network of hybrid orbitals is well defined. So the first thing we have to assume is that hybrid theory gets us most of the way there, right? The hybrids, this is going to do a good job of describing the individual bonds, the single bond part. Second thing we have to assume is essentially this single bonded network is going to create some electrostatic interaction. So this is an approximation to the Hamiltonian. The electrons not in the hybrids experience a fixed electrostatic field due to the hybrid orbital electrons. In my opinion, this is one of the most important things in Huckel theory. Not necessarily just for Huckel theory. This kind of idea of assuming that there's a cloud of electrons that we can assume is there in static is also part of what's built up density functional theory. This is kind of one of those underlying principles. And density functional theory is kind of the newest and greatest approximation methods for solving problems, particularly for condensed phase. And it really has this kind of idea in it where you've got some fixed electron cloud interacting with like the outer electron that you're trying to approximate. The third thing is the electrons not in hybrids are delocalized. Three assumptions we need to make. These three assumptions, and I've been using relatively broad terms in terms of electrons in hybrids, electrons not in hybrids. We usually give those two sets of electrons different names based on the rotational symmetry that we experience with them. So single bonds, like this, they have this rotational symmetry associated with them. We call those sigmas. The electrons not in hybrids, those ones that are going to be in the unhybridized orbitals, those have a different symmetry associated with them. The cases we're going to be looking at, that's going to be a particularly the py orbital is left over. That is going to give rise to the not in hybrids, which are going to be called pi electrons. So this idea that it's a conjugated pi system, we're really looking at those not hybridized orbitals on neighboring carbons. This trick, Huckel theory, essentially lets us split up the problem, right? If you think about a bunch of carbons, each carbon center has a nucleus that's going to be interacting with the electrons. There's going to be a lot of electrons. This trick lets us split up, essentially, the electrons that are in hybrids as a separate problem from the electrons not in hybrids. We get to treat the sigma electrons completely separate from the pi electrons. Is that true? Not really, right? This is an approximation. This is going to be something that allows us to simplify what we have to solve. So this means, the nice thing about that is it also means we only need to do these pi electrons. So when we start looking at the carbon network, we start thinking about which electrons are in hybrids, which ones are outside of hybrids. We really just have to focus on those leftover p electrons. So we're only going to be looking at essentially the py orbital. And that's the only thing we're going to have to be concerned about. So let's go ahead and see how we set up one of those problems. I'll see, I have time to, I think, set up one of them and kind of lead you to thinking about another one. Question?
I just wanted to double check. Like the ones in hybrids are sigma, they're not pi.
Yeah, the ones in hybrids are sigmas. The ones not in hybrids are pi's. So the sigmas are the ones that are directly connected with each other, have that rotational symmetry. Did I write something wrong up there someplace?
No,
Okay. So we could go through. Maybe this will make our lives a little bit easier. We can go through and we can relabel this and say pi electrons are delocalized. Pi electrons experience a fixed electrostatic field due to the sigma electrons. Right? That makes the sentences read a little bit better, but only if you know what sigma electrons and pi electrons means. So, the simplest system we can do is this one, where we only really need to focus on the fact that one of these, this is our representation of this, but essentially we can imagine this is described by a hybrid, and all we actually have to worry about, and I apologize for my three-dimensional drawing capabilities, but all we have to worry about is that leftover p. That's the only thing we have to worry about. Now, for this simple case, we're going to get something that looks really familiar. That is to say, we can look at this and we can essentially get psi for the pi electrons is going to be equal to some constant 1 psi 2py on carbon A plus some constant 2 psi 2py on carbon B. This looks exactly like the problem we did last time, except for now we have p orbitals instead of s orbitals. Right? This is two constants, two wave functions, seeing some interaction associated with those constants and those wave functions. So I hope you all have a sense of what's going to happen next when we have this guess function. We get this. The same type of thing that we saw before. And we're going to do a lot of the same tricks that we did before. Namely, we're going to say h11 is some integral. We'll solve that later. However, we call it something different this time. This time, and it is because it's particular to Huckel theory. h11 is essentially going to be this integral. It's going to be something like that. The problem is assumption number 2. Right? Writing down this integral is going to be quite a bit more complicated, writing down this Hamiltonian is going to be quite a bit more complicated, which shouldn't be that surprising to us because we have a lot of electrons in that sigma network. Still, we call this integral, we just set it equal to some thing that we're going to solve later, alpha, which is going to be called, and I was frustrated by this, but it's essentially your Hamiltonian is going to be some kinetic energy part plus some Coulomb part. Where that Coulomb part's due to all of the sigma electrons. In this case, this is again called a Coulomb integral. I'm putting in quotes, and I apologize because it's a different Coulomb integral than the one we did before. Pretty much any time you have an integral that's dominated by the Coulomb force, we call it a Coulomb integral. So we can go ahead and replace our H11s with alphas. And our H22, if I just switch this so it's BB, it's the same integral, right? Same thing we did before when we were looking at just the H2 plus case. We're going to have the same thing. Our diagonal elements are the same. We're also going to have the same thing since we're using a normalized set of wave functions. I should actually write that up just so we're clear. S11 equals S22 equals the integral. Let's just do the S11 first. The S11 integral is going to be the integral of a psi 2py a star psi 2py a d tau. And if we're in a normalized basis set, that's just equal to 1. So we can essentially just erase those two. Now, there's some extra approximations that we put in for Huckel theory that we've historically put in to make it easy to solve that we don't put in anymore. That is essentially related to this last integral we have to write down, H22. So H12. In H12, it's very similar to what we did before. H12 and S12 are the two that we still have to do. H12, we're going to have the same thing, except it's going to have an A and a B. But the thing I really want to get to is the S12. Because we're going to have an S12 in the H just like we did before. The thing that we often do in Huckel theory is we assume that's 0. Now, there's some rationale to why we get to assume that's 0. It has to do with looking at 2p orbitals that are separated by some internuclear distance. So remember, when we solved this for the p orbitals, we got something that just depended on the internuclear distance. We're going to get something like that again. And in fact, I was really impressed with your book, which I know you're all like, but there's actually, they have the overlap integrals for the other types of interactions. If you have the 11th edition, it's table 9C1. It has the S overlap, the 1S, 1S overlap that we did last time. It also has the 2S, 2S overlap, which looks similar. Then it has the 2p pi overlap, which is the one we're looking at now. And it also has the 2p sigma overlap, which we would look at if we were trying to make better sense of this integral. So I'm out of time, but I'm so close to doing the interesting thing that I kind of want to keep going, but I can't actually keep you anymore. So I'll do the same thing I did last time, which is eventually what I'll show you at the beginning of class next time is we can write down this integral. We're going to call this H12 some integral that we're just going to call beta. That's going to be what's called the resonance integral. And then we're going to diagonalize that matrix. And I have a little MATLAB program to show you that. But man, it's going to be a while. So you're going to have to remember this. Just a reminder, we don't have class on Monday. On Tuesday, we're following a Monday schedule. So our next class is until Thursday. So our next class is in a week. and it's our midterm. So that's unfortunate, but we all voted on this. So you know, if you're like surprised, remember we all voted for this to happen. So you bought into this.
Is that beta for like that whole equation?
So that beta is really just going to be this.
And that's something else.
For our
assume
simplest case of Huckle theory, we assume that
so it's beta plus 0 or minus 0. Okay.
Beta minus 0. In truth, most computational people don't assume that's 0 anymore because we can just solve the integral.
Because we can like do it computationally.
Yeah, but original Huckle theory assumed that was
For our
0.
methods, we're doing 0.
Yeah.